Good afternoon. We're going to go through this particle thing again because I don't know. I sort of don't remember how that last one went, and I just felt like we could take some time with it. It felt maybe a little rushed, but maybe it wasn't, and I'm just boring. Anyways, quarks. So you can look it up. There's basically two kinds of quarks. There's generations of quarks that are sort of somehow larger, more massive. And we can talk about that maybe in the future, but fundamentally things are made out of two kinds of quarks. At least matter in our world is made out of two kinds of quarks, the up quark and the down quark. And then there's an anti-up and an anti-down. So this would be an up quark. Ooh, this is an up quark. I do blue for positive. So it's got two positive, 2/3 positive charge, two axes, positive charge, and then there's the downs, which has one axis of negative charge. So this is one, and this is a quark. This is a quark. This is a quark. I just have them in pairs for convenience, for quark math. So this would be an up quark, and the way you make a proton is you take an up quark, and we'll take this and we'll turn this into another up quark. Put this aside for now, and a down quark. There we go. So these are the elements for building a proton. And I say, cool. Okay, so how are we going to do this? And I figure, well, let's take this, and I'm going to squish them together. And I'm going to make, using a positron and an electron, I am going to make a photon. A little tiny photon. It's exactly Planck size. And therefore it's trapped over its own gravity. So this is a mass unit now. I just turned that photon, that was those charges, into that. And now I still have 3 of these blue things. Well, I could take this, and this goes like this, and fits in here. And this makes a nice, 3 axes, which is sort of cubic in the one way and octahedral in the other way. If you fit the triangles in those things. But this works very well for quaternions and all that sort of thing because everything's 90 degrees. So if you modify that, this charge would go there. If you modify that, this charge would go there. Oh, funny. And then this green one I'm going to shove inside as well. And there we go. That's a proton, which is a mass unit surrounded by 3 axes of positive charge. So that's how you would build a proton. And this, I think, is a much more sensible way of looking at it than those up, down things for kids even, because now it's like, okay, we've got this whole, the quaternion twisty thing, 90 degrees, 90 degrees, 90 degrees. And it accounts for all the math really nicely. So there we go. So now if we wanted to build a neutron is one of those, 1 up and 2 downs. And what I'm going to do is, actually, let's trade these for this. One up, 2/3, 2 downs, 1/3, 1/3. And what I'm going to do with this is I'm going to take this and this, and I'm going to do that same thing where I'm going to turn this into a tiny mass unit photon. Mass unit photon. I'm going to take this and make it into another mass unit photon. It's going to lay on top of the other mass unit photon. But because this doesn't quite fit, it's got a perturbation on it and only lasts 10 seconds on average. But then, interesting thing, that if you have one of these, a neutron, 2 photons. One photon, two photons. One photon makes a mass unit. Second photon makes a double layered mass unit. But because the one was perfect and this is slightly too big, it develops perturbations and decays. But when it decays, what does this turn into? Generally, what it turns into actually is a proton and an electron, plus a neutrino. Which seems like some pretty good math, because this is like 2 charge units, and this is 2 charge units. So that was 4 charge units. And now you've got 1, 2, 3, 4, 5, 6, 7, 8 axes of charge somehow out of this deal, plus a neutrino. But the neutrino was probably incorporated. You probably would have wanted 2 neutrinos to make those math units. But there we go. So I just think, but look at this. It gives us, here's our electron. Again, now it's just sitting around. You impose a magnetic field on it, right? All of a sudden, it's going to rotate. You're imposing a geometry on it, and therefore it has to pick one spin or the other. Here's our proton. Basically, one is the reciprocal of the other. This would be like a ginormous one that's larger and would be surrounding this, like the big spheres that fit in these holes sort of thing. This would be surrounding this and obscuring this, but perfectly balances it. There we go. But now all of a sudden, geometries make even more sense in terms of how quarks fit together to build things, don't you think? I don't know. I think so.